Hello guys, and welcome to another calculus video. In this video we're going to be taking on this awesome integral right here. It's the integral from 0 to infinity of ln x over x plus 1 times x squared plus 2x plus 1 minus a squared, or you could also rewrite this as x plus 1 squared minus 2a squared. And we're only looking at values for where a is between 0 and 1, so we won't have any sort of principal value or anything that we have to deal with. So this is actually, the reason I'm solving such a kind of random integral at this time is because it's actually a lemma for the big integral that I solved that I spent 2 months on, and so we're going to have to go ahead and solve it before I can go ahead and present that. So we're going to be using a few theorems right here. First off, this integration formula, the integral from 0 to infinity of x to the k over x to the n plus 1 dx, equals pi over n cosecant k plus 1 over n times pi. This is something I've used in many videos before, so it's going to be used again today as well, and I've proven it in several previous videos also. We also have this expansion for cosecant of x, which is the Laurent series actually for cosecant of x, and cosecant of x equals 1 over x plus 2 times the sum from k equals 1 to infinity of x to the 2k minus 1 over pi to the 2k times eta of 2k. We're going to be using this. This I proved in, I believe, my latest video, or maybe it was 2 videos ago, on the sum of inverse hyperbolic cotangents. So we're going to be using those. So the first thing we need to do when splitting up this integral is we're just going to split it up into several different parts using partial fractions. So I've gone ahead and done that. We're going to end up with this. And as you can see, we have ln x times a bunch of constants over x plus some other constants, right? And so we're going to want to try and apply this formula right here. And so the way we're going to do that is we're going to consider I of v, this is a function of v, which is going to be 1 over a squared times the integral from 0 to infinity of x to the v, and rather than ln x times all these functions. So I just factored out that 1 over a squared. And then notice that if we differentiate I of v with respect to v, we get an ln x out of there, right? And so that means if we take the limit as v goes to 0 from the left of I prime of v, then that's going to give us just this original function right here, which is what we're trying to integrate. And the reason we have to approach from the left is that if we approach from the right, it becomes hard to use this formula. I mean, we can still use the formula, but it becomes a little bit harder to actually show that it's going to converge, which we know it is going to converge. So I just like to take the limit from the left because that just is a little bit easier, and the actual process for evaluating the limit is exactly the same. So we're going to define another integral function right here, j of v and alpha. So it's going to be two different variables right here, and we're just using this to facilitate our calculation of these three separate integrals, x to the v over x plus 1, x to the v over x plus 1 minus a, and so on and so forth. So this integral j is going to be the integral from 0 to infinity of x to the v over x plus alpha dx. And in this case, alpha is greater than 0. So we're making the substitution x equals alpha u, and after we go ahead and factor everything out, we get alpha, this should be v, I don't know why it says t right here. So we just end up with alpha to the v times the integral from 0 to infinity of u to the v over u plus 1 du, and just go ahead and plugging that in, we get this, and then simplifying because cosecant of pi plus x is just negative cosecant of x, we get that our integral j of v and alpha is negative alpha to the v times pi cosecant pi v. Then we go ahead and this looks kind of daunting, but all I did was I just went ahead and plugged in our definition for j of v and alpha and our function I of v up here. So you see we have minus 1 over x plus 1 plus 1 half x plus 1 minus a, so that just matches up with everything down here. So we have negative 1 over a squared times negative j of v and 1 plus 1 half j of v and 1 minus a plus 1 half j of v and 1 plus a. When we go ahead and plug in our definition, which is right here for j of v and alpha, we get pi over 2a squared times cosecant pi v times this nice little expansion right here. And again, we're going to differentiate I of v with respect to v, but we're not actually going to go ahead and perform that differentiation. We're just going to go ahead and write this as the derivative of this, and you'll see why in a moment, because if we differentiate this, we'd end up with some nasty product rules, like some cosecant and cotangent, which becomes very, very hairy to deal with. But you're going to see the method that we have to solve this limit very, very quickly and easily without having to deal with cosecant and cotangent and all sorts of nasty functions and L'Hospital's rule. So as we take the limit as v goes to 0, again I have a t in here, sorry about that, but really it's limit as v goes to 0, and reminder that limit as v goes to 0 minus of I prime of v is just our original integral. We get this nice limit, pretty much the same thing as before, and now we're going to figure out how to actually evaluate this. And so, as you can see here, as v goes to 0, these are both going to go to 1, and so this is just going to go to 0, as well as this is going to go to 0, and both of these are going to be first order zeros. So one way that we can facilitate the evaluation of this integral in a little bit of an easier way is expand everything as a power series, and we're going to truncate all these power series at the order of v cubed. So we know that 1 plus a to the v is going to be 1 plus ln 1 plus a times v, just differentiating this function with respect to v and then evaluating it at 0, and then ln squared of 1 plus a times v squared over 2, plus anything of order v squared, v cubed and above. Pretty much the same thing for 1 minus a, and for cosecant of v, we're going to use that definition that I showed you at the top, and when we go ahead and do that, we're going to end up using eta of 2 right here, and we're going to eventually, once we plug everything in, we're going to get 1 over pi v plus pi v over 6 plus anything on the order of v cubed and above. And the reason I'm ignoring anything on the order of v cubed and above is because, again, we have a first order 0 here, a first order 0 here, so anything above the order of v squared is really not going to be important, because we would probably only have to use L'Hospital's rule once or twice in order to evaluate this. So when we go ahead and plug everything in, we get pi over 2a squared times the limit as v goes to 0 minus of the derivative with respect to v of 1 over pi v plus pi v over 6 times this nasty extension of a bunch of natural logs, which really does not look very fun to deal with. However, let me convince you that this actually isn't so bad. And the reason it's not so bad is, if we think about it, we're going to take the derivative with respect to v, and then we're going to evaluate it at v equals 0, essentially, right? So if you think about it, anything that after we differentiate it is of order v or above is just going to go to 0, because we're taking the limit as v goes to 0. And any constant terms right now are just going to end up getting differentiated, and so they're going to disappear. And as you can see, we're not going to have any terms of value less than 0, because this 1 over pi v is counteracted by this v and this v squared. So the only term that we care about is the term that has a coefficient, or the coefficient of v in the overall expansion of this. So actually this pi v over 6 doesn't end up mattering, and we just have 1 over pi v times negative 1/2 of this nasty stuff with the natural logs times v squared. And we're going to ignore everything else, because either it's going to get differentiated out, or once we differentiate and we go to 0, it's just going to disappear as well. So we just have the limit as v goes to 0 minus of the derivative with respect to v of negative ln squared of 1 plus a minus ln squared of 1 minus a all over 2 pi. That 2 pi just comes from this pi right here and this 2 right here, all times v. When we differentiate with respect to v, this v is just going to disappear, and then the limit as v goes to 0 of constant is just that constant. And so overall, our integral, once we cancel out this pi, and we combine this 2 and this negative sign, we're going to get that this integral is equal to negative 1 over 4a squared times ln squared of 1 plus a plus ln squared of 1 minus a. And this may seem like kind of a wacky result for a not too interesting integral, but again, as I said, this is actually a lemma for an incredibly, incredibly fun integral that I'm going to be evaluating in our next video. Should be a pretty long video as well as a very fun one, so I hope to see you guys in that one. And if you guys have been keeping up with my channel, you know that I'm actually planning on making a switch in my channel. So after I release that video, I will be sort of alternating between releasing cool integrals, as I've been doing, and releasing videos that are sort of an integration guide for beginners and intermediates and advanced, for everyone to learn how to get better at integration, to do the same sorts of things that I do in my videos. So please stay tuned for that if that's something that sounds interesting to you, and thank you for watching. I hope you enjoyed this video, and I'll see you next time.